Hi, I am Kaushik Hasabnis. Today I will give the short overview of my project. My project is on digital twin network for batteries. It is under the guidance of Dr. T.V. Prabhakar sir. Digital twin is the virtual replica of the physical system. Here for the battery, digital twin is the virtual replica of the physical batteries. It keeps the real world and the virtual world in the synchronization, as well as it will keep the real time monitoring of the battery. So as you can see here, we are taking the number of cycles, discharge profile and temperature from the real world battery to our digital twin model, and our digital twin model will predict the state of charge, state of health, voltage and current state in the virtual world. So this is functional block diagram for our system. Data is generated from the battery system. This data need to be sensed. For this purpose, our sensing unit has three parts. First part is the main PCB, which senses the voltage, current and state of charge of the battery. Second part is the thermal imaging of the battery. Hotspot will be detected from the thermal imaging and then the over temperature signal will be generated. For this purpose, FLIR Lipton 3.1R camera is used for the thermal imaging of the battery. Third part is the number of cycle tracking. For this purpose, RPI camera and a QR code is used. RPI camera will scan the QR code and it will access the number of cycles of the battery and then update based on the current number of count. So this data is further need to be sent to the remote client. For this purpose, battery will be IoTified using the OPC publisher. OPC publisher gives the data access, history data access, and the alarms and events. So from the OPC client, we can access this data, history data of the battery, and this data will be further sent for the model creation and data visualization. So based on all available data and the history data, model of the battery using the RC model of the battery is created for estimating the terminal voltage and state of charge. So as you can see here, these are the results which are taken from our hardware system for the data sensing. You can see here cell 1, cell 2, individual cell voltages are given. Total battery voltage is also indicated. With that, we have the current sensing also in positive and negative, that is charging and in discharging direction. Here state of charge also will be indicated. So this is the sensed data from the battery which will be further sent to the OPCUA publisher. These are the some FLIR camera images which shows the whenever battery get heated, the hotspot of the battery in the yellow colors and the battery is cold in the right image. So barcode based cycle count is works using this algorithm. So firstly we will scan the QR code, then it will get connected to the MQTT topic. From there we will subscribe our present count of the battery. Then if the battery is again placed back to the original circuit, then check the voltage that battery is reached the final charging point, that is the for the 12-volt battery it will be the 12 volt. It depends on the battery voltages. Then we need to increment our count if battery is charged and then again publish back to the same MQTT topic. So this will be the industrial design for our complete project. Now we have all the data of the thermal FLIR camera image, that is over temperature indication, then voltage, current, state of charge, and the number of cycles of the battery. So this data need to have the remote access for IoTifying the battery. So for this purpose, we are using the OPC UA, that is the Open Platform Communication Unified Architecture. It is open source IEC 62541 standard for the data exchange. It is the communication protocol independent and it will map to the several protocols, that is the TCP/IP, UDP. So OPC publish subscribe architecture is demonstrated in this image. So we have the our lithium ion battery from the EVs, which we are connecting our OPC server. OPCS or server has the address space in which the data will be collected and stored. So this is in the specified way that all this OPCUA has each nodes. This node has each specific identification numbers and the display values. So in the dataset collector, we are taking the battery number, voltage, current, state of charge, cycle and temperature data, which will be used as a published dataset. With this, we are adding the metadata with which is used for the dataset writer ID, and it will be dumped into the JSON format. So if we have two or more batteries, then the dataset writer 1, writer 2, like this will be come into the picture. Then again, all this data will be sent over the MQTT to the message oriented middleware. And from the client side, this will be decoded in the reverse direction. So our OPCUA information model is gives us the data access, which shows the representation of variable in the for the continuous data acquisition, which is the main part of the digital twin, that is the replicating the real world values and keep the real world and the virtual world in the synchronization. Also, the historical data access is provided from the OPCO information model, which is also the important for creating our model. With this, also the alarms and the events, conditions and the different programs can be run from the OPCUI. So OPCUI will give mainly here for digital twinning data access and history data access, and from this we can run our custom information model based on this for creating the virtual copy of our battery. So you can see the results of the OPCUI information model here. So this is the graph of the history data. You can see different graphs for the different values. As I have told, we have specified architecture for the OPCUA nodes. So OPCUA has, each node has its own unique node ID. Also, it has its own display name, which is correspond to from the our corresponding server. So this is the data access view in which we can see the current display values of the OPCUA, all the nodes with the server timestamp. Also, we can access this data from our OPCUA Python client also. So the decrypted JSON data is also shown here. So we have the message ID, type of the data, and the dataset writer ID also here. With this, a payload with the voltage, current, state of charge with all the actual values will be sent over the MQTT. So this is the OPCUA PubSub configuration implemented for the IoT paying battery and giving the data access and discrete data access to the remote client. Now this data will be sent to for the modeling. So firstly, we have to implement the our battery cycling for getting the data from the battery. So here a CLTC cycle will be used for the accelerated battery aging profile. Here for this profile, low speed range is 37.4%, medium speed range is for 38.5%, and the high speed range is for 24.1%. This accelerated battery profile, current profile is applied to our battery and data will be collected from the battery. So corresponding voltage, time, duration, loading of the battery is shown here. This is for the 4 cycles of the CLTC run back to back. So based on the previous data collected, we are implementing the model for the battery. So model for the battery is, it has the internal open circuit voltage in series with the R0. This R0 also indicates the health of the battery. As the battery ages, this R0 value will increases. So next is the R1 and C1 and R2 and C2. These are the transient parameters for the battery charging and the discharging. So total terminal voltage V of T of the battery is the open circuit voltage minus the voltage across R1 C1, R2 C2 and the R0 pair. Then state of charge has the formula of the state of charge of the at the zero time minus the what is the charge drawn from the battery. Now R0 is calculated by finding the current profile, that is whenever there are instant accelerated current changes, there are a drop in the voltages. So from Vmax minus Vmin divided by Imax minus Imin, we are calculating the R0. Now R1 C1 and R2 C2 will be calculated using the curve fitting from the previous equations. So from this the state transition equations can be written, and this is the A matrix, this is the B matrix, and C and D matrix can be calculated from the output equation. From this, the prediction step, measurement update state update, and covariance update for the Kalman filter is implemented. And from this, the A, B, C, D matrix and all the parameters of R1, C1, R2, C2, and R0 of the battery, the current state of charge of the battery will be predicted. Also, the terminal voltage of the battery will be predicted. So these are the results of the Kalman filter estimation, the predicted and measured voltage. So this is the predicted and measured state of charge of the battery. So we can See here, our predicted and measured results are within the range of 0.5% error. Also, for verifying the UDDS current cycle will be applied to the battery, and same type of results, the measured and predicted using the Kalman filter, will be tracked. So continuous cycling of the CLTC cycling will be done, and the results we can see here, the voltage versus state of charge of the battery. So as the battery ages, the we can get the less current total charge from the battery. So that is, the battery capacity gets reduced and the R0 value also increases. So that can be seen from this one. So this is the complete project. So our project has mainly three parts. The first part is the hardware sensing from the battery. Second is the IoTifying of the battery, which is the OPC UA part. From the OPC UA communication, OPC UA architecture, we are sending our complete history data access to the remote client in the unified architecture way. This data will be further used for cleaning the battery in the virtual world. That is, we are creating the model and predicting the state of charge and voltage based on the Kalman filter implementation. Thank you.